Good day, everybody. How are you all? Today we are going to talk about chapter 9. So, without further ado, let's get started. Give me a minute. Inference about the difference between two means independent samples. So, these are the objectives independent and paired samples. A drug company has developed a new drug that is designed to reduce blood pressure. The researchers wish to design the study to compare the effectiveness of the new drug to that of the old drug. Here is one way in which the study can be designed. Two samples of individuals are chosen. One sample is given the old drug and the other sample is given the new drug. After several months, blood pressure of the members of both samples are measured. We compare the blood pressure in the first sample to the blood pressures in the second sample to determine which drug is more effective. In this design, samples are independent. This means that the observations in one sample do not influence the observations in the other. So one sample was given the old drug, the other sample was given the new drug. So what we observed in sample 1 did not influence what we observed in sample 2. Paired samples, here is another way in which the study can be designed. A single group of individuals is chosen. They are given the old drug for a month and their blood pressures are measured. Then they switch to the new drug for a month, after which their blood pressures are measured again. Notice in this, the groups of individuals in the two situations. One, the first month of old drug, second month of new drug, they're the same people. Only their blood pressures are measured at the end of the month for, consuming old medicine, and then their blood pressures are again measured at the end of month 2 when they took the new medicine. Okay, so they're linked to each other. Okay, we compare blood pressure in the first sample to the blood pressure in the second sample to determine which drug is more effective. In this design, the samples are paired. Why? Because they're same individuals on which two sets of measurements are made on two different conditions. Each observations in one sample can be paired with the observation in the second. Check your understanding. Sample of students is enrolled in a speed reading class. Each takes a reading test before and after. Again, after the class, the two samples of the sources are compared to determine how large an improvement in the reading speed occurred. Are these samples independent or paired? Okay. So this is paired because the same group of students that their proficiency are measured at the beginning of the speed reading class and then at the end of the speed reading class. So paired measurements. And then next one, part B, sample of students is enrolled in an online statistics class. Another sample is enrolled in a traditional statistics class. At the end of semester, the students are given a test. The scores from each sample are compared to determine which class was more effective. Are these samples independent or paired? These samples are independent because there are two completely different groups of students and they got two different kinds of treatment. One got the regular lecture and the other attended the online class. So two different groups of sample, they're not connected, or subjects, they're not connected to each other. Therefore, these are independent samples. Okay. Perform a hypothesis test for the difference between the two means using the p-value method. We begin with an example. Scores on the National Assessment of Educational Mathematics at the test range from 0 to 500. In a recent year, the sample mean score for the students using a computer was 309 with a sample standard deviation of 29. Okay. Okay. For students not using a computer, the sample mean was 303 with a sample standard deviation of 32. Assume there are 60 students in the computer sample and 40 students in the sample that did not use a computer. We can see the sample means differ by 6 points. Now we are interested in the difference between the population mean. Is it plausible that the difference between the population means could be 0? That is, null hypothesis mu1 minus mu2 equal to 0, and alternate mu1 minus mu2 not equal to 0. How strong is the evidence that the population mean scores are different? This is an example of a situation in which data consists of two independent samples. Two samples are independent if the observation in one sample do not influence the observations in the other. The issue is whether the mean scores from both populations of the students, those using computers and those without the computers, are equal. In other words, does mu1 equal to mu2? So null hypothesis is mu1 equal to mu2, alternate, the three kinds of alternate. If H1 is mu1 less than mu2, that is a left tail test. H1 could be mu1 greater than mu2, that's a right tail test, and H1 could be mu1 not equal to mu2, that's a two tail test. Notation mu1 and mu2 are the population means, x1 bar and x2 bar are the sample means, s1 and s2 are the sample standard deviations, n1 and n2 are the sample sizes. So, the test statistic is based on the difference between the two sample means x1 bar minus x2 bar. The mean of x1 bar minus x2 bar is the population mean differences, that is mu1 minus mu2. We approximate the standard deviation of x1 bar minus x2 bar with a standard error. So basically, we calculate a test statistic where we compare the difference in the sample means with the hypothesized difference in the population mean. So in the T, the term in the numerator, first term in parenthesis, is the difference in the two sample means. That difference is being compared to the hypothesized population mean difference, which is the term in the second parenthesis. The whole numerator is divided by the standard deviation of the sampling distribution of S1 of x1 bar minus x2 bar. And degrees of freedom, in this case, smaller of n1 minus 1 and n2 minus 1. The method just described requires the following assumptions. We have simple random samples from two populations. The samples are independent of one another. Each sample size is large, or its population is approximately normal. Okay. So state the null and alternate. If making a decision, choose a significance level alpha. Compare the test statistic. We do not have to remember the formula. Formula is built in the calculator. Compute the p-value. Interpret the p-value. If p-value is less than alpha, reject H0. If p-value is greater than alpha, fail to reject H0. State a conclusion. This they show how to calculate the p-value. Okay. So this is the problem that we encountered before. The National Assessment of Educational Progress tested a sample of students who had used a computer in their mathematics classes and another sample of students who had not used a computer. The sample mean score for students using a computer was 309 with a sample standard deviation of 29. For students using a computer, okay, so the first one is sample mean score for students using a computer was 309, sample standard deviation is 29. For the students not using a computer, sample mean was 303 with a sample standard deviation of 32. Assume that there were 60 students in the computer sample and 40 students that hadn't used the computer. Okay. Can you conclude that the population mean score differ? Use alpha equal to 0.05. We can call 1, okay, as the group which did not use a computer. Or, yeah, or let's call 1 is the group that used a computer. So their mean was 309, x1 bar is 309, s1 is 29, and let's call 2 the group which did not use a computer. X2 bar is 303, S2 is 32, N1 is 60, and N2 is 40. Okay. So let's go to our calculator on stat test. We go down to two sample t-test. Okay. Input is on stats. X1 bar is the sample mean of the group that used a computer, which is 309. Okay. SX1 is 29. N1 sample size of the group using computer, 60. X2 bar is 303. SX2 is 32. And N2 is 40. Our alternate is not equal to mu2. Pooled, we will say no always. That means we are not assuming that the population standard deviations of the two situations are equal. So pooled no means we are assuming that the population standard deviations of the two different groups are not equal. Okay, pooled is no, and we go to calculate. Our alpha is 0.05. We will calculate a test statistic and a p-value. The test statistic is 0.953. P-value is 0.343, which is greater than alpha equal to 0.05. Hence, the decision is do not reject H0 because P is greater than alpha. And conclusion is that alpha equal to 0.05. There is not enough evidence to support H1, the alternate. Okay. So what was it? P is greater, we do not reject H0. Okay. P is 0.343. That's what we got. P is 0.343. Okay. Test was made of H0 mu1 equal to mu2 versus H1 mu1 not equal to mu2. Independently random samples were drawn from approximately normal population. Sample means were x1 bar 73.9, x2 bar is 72.8. Sample standard deviations were S1 4.2 and S2 is 3.8. Sample sizes N1 is 23 and N2 is 17. Find the value of the test statistic and decide whether to reject H0 at alpha equal to 0.05. So stat, test, two sample t-test. We do not use two sample z-test because we do not know the population standard deviation. So x1 bar is 73.9. SX1 is 4.2. N1 is 23. X2 bar is 71.8. SX2 is 3.8. N2 is 17. Okay. And the alternate is mu1 not equal to mu2. So it should be flashing on not equal to pooled mu2. Pooled is no always. And we calculate the test statistic is 1.651. P-value is 0.107. P-value is greater than alpha. Decision do not reject H0. At alpha equal to 0.05, there is not enough evidence to support the alternate hypothesis. Perform hypothesis for the difference between two means used. No, I'm not going to critical value method. So we'll skip this. Construct a confidence interval. Imagine that we will compare a new blood pressure drug. This is the same situation as before. Let's go to this problem. Okay. Okay, let's go to this problem. This is the problem, right? Blood pressure problem. Did we see this before? They did not give us any. Okay, so we'll go back to this problem. Okay, critical value method is not, we are going to not cover. Construct confidence interval. Okay, imagine that we will compare a new blood pressure drug. So we are going to calculate confidence interval of the difference between two population mean. Imagine that we will compare a new blood pressure drug to a standard drug. We will draw two independent samples. The first will get the new drug and the second will get the standard drug. We can imagine that these samples as coming from two populations, a population of patients who take the new drug and a population of patients who take the standard drug. For each population, there is a mean reduction in blood pressure. We are interested in estimating the difference between the population means. Let mu1 be the population mean reduction for new drug and mu2 be the population mean reduction for the second drug. We used to construct a confidence interval for difference mu1 minus mu2. The point estimate for the difference mu1 minus mu2 is the difference between the sample means. In other words, point estimate for mu1 minus mu2 is x1 bar, which is sample mean of sample 1 minus sample mean of sample 2. Okay. So the sample means x1 bar and x2 bar have variances sigma 1 square divided by n1 and sigma 2 square divided by n2. When the samples are independent, the variance of the difference in x1 bar minus x2 bar can be shown to be the sum of the variances. In other words, the variance of x1 bar minus x2 bar is sigma 1 square n1 plus sigma 2 square n2. The standard error of x1 bar minus x2 bar, remember that is the standard deviation of the sampling distribution of x1 bar minus x2 bar, is the square root. Since we don't know the values of sigma 1 square and sigma 2 square because these are population variances, we approximate them with sample variances s1 square and s2 square. Therefore, the standard error is given by square root of s1 square divided by n1 plus s2 square divided by n2. So, critical value for the confidence interval is T alpha by 2 based on the student's T distribution. There are two ways to compute degrees of freedom, a simple method for computing by hand and a more complicated method by software calculators. Simple method is degrees of freedom smaller of n1 minus 1 and n2 minus 1. Margin of error is obtained by multiplying the critical value of T with the standard error. Confidence interval is x1 bar minus x2 bar plus minus margin of error. This method is often referred to as Welch's method. Assumptions. The method just described requires the following assumptions. We have simple random samples from two populations. The samples are independent of one another. Each sample size is large and greater than 30 or its population is approximately normal. Okay. So here it is. A drug company has developed a new drug designed to reduce high blood pressure. To test the drug, a sample of 15 patients is recruited to take the drug. The systolic blood pressures are reduced by an average of 28.3 millimeters of mercury, with a standard deviation 12.0. In addition, another sample of 20 students takes a standard drug. The blood pressure in this group are reduced by average of 17.1 millimeter mercury with a standard deviation of 9. Assume that the blood pressure reductions are approximately normally distributed. Find a 95% confidence interval for the difference between the population mean reduction for the new drug and that of the standard drug. So they want us to find out a 95% confidence interval for the difference in the population mean mu1 minus mu2, where 1 is a group of patients who are taking the new medicine, 2 is the patient who's taking the standard drug. So we first check for assumptions. We have two independent random samples and the populations are approximately normally distributed. The assumptions are satisfied. So now go to our calculator, stat, test. We are scrolling down to 2 sample t interval. T because we do not know the population standard deviation. Number 10. Input on stats, x1 bar is 28.3, sx1 is 12, n1 is 15, 15, x2 bar is 17.1, sx2 is 9, and n2 is 20. Okay, n1 is 15, n2 is 20. Okay, and sea level is 0.95, pooled no, and we calculate. Notice the lower boundary is 3.59, upper boundary is 18.81. Both of the numbers are positive. They're on the right side of 0. That means mu1 will be always greater than mu2. Okay. Therefore, we can remember if we do this problem, hypothesis test, null hypothesis will be mu1 minus mu2 equal to 0, alternate mu1 minus mu2 not equal to 0, or null hypothesis will be mu1 equal to mu2, alternate mu1 not equal to mu2. Now we have calculated an interval, 95% confidence interval for the difference in population mean, which starts from 3.59 and ends at 18.81. So mu1 minus mu2 is always positive. That means mu1 is always greater than mu2. Hence, we can reject the null hypothesis and support the alternate hypothesis. Okay. A sample of 87 one-year-old spotted flounder had a mean length of 126.31 millimeters with a sample standard deviation of 18.1 millimeters with a sample of 132 2 years. So first was 1 year, next was 2-year-old spotted flounder. Mean length of 162.41, standard deviation is 28.549. Construct a 95% confidence interval for the mean length difference between 2-year-old flounder and 1-year-old flounder. Okay, so 1 we can call as a 2-year-old flounder, 2 we can call as 1-year-old flounder. Okay, so let's call the 2-year-old flounder, okay, as 1. Okay, so and 1-year-old flounder as group 1. Okay, so stat test. We crawl down to 2 sample t interval, hit enter. Input stats, x1 bar is the, why am I calling the 2-year-old flounder as 1? Because we want to find the difference between 2-year-old flounder and 1-year-old flounder. Of course, the 2-year old flounders are little longer in length. So 1 we will call the 2-year-old flounder. So the mean is 162.41. Standard deviation is 28.49. N1 sample size is 132. X2 bar, okay, 126.31. SX2 is 18.1. And N2 is 87. Okay, it's the 1-year-old flounder. Sea level is 0.95. Pooled is no. Calculate. Okay. Let me see. Stat. Test. 2 sample t interval. 162.41. 28.49. 132. And X2 bar is 126.21. 126.21. SX2 is 126.31 actually, 126.31. And SX2 is 18.1, N2 is 87, okay, and 95, and pull this no, and we calculate. So it is between 29.894 and 42.306. Yep. Okay. We will skip over this. When two population variances sigma 1 and sigma 2 square are known to be equal, there is an alternate method for computing a confidence interval. This alternate method was widely used in the past and is still an option in many forms of technology. However, it is not recommended. The major problem with this method is that the assumption that the population variances are equal is very strict. And the method can be quite unreliable if it is used when the population variances are not equal. So we'll just forget about it. So we are done with this section. We will jump to the next section now, which is 9.2. I hope this is this one. Yep. Inference about the difference between two means, paired samples. Perform a hypothesis test. Perform a hypothesis test with a matched pairs using the p-value method. A sample of 8 automobiles were run to determine their mileage in miles per gallon. Then each car was given a tune-up and run again to measure the second time. So they're the same cars after the tune-up and before the tune-up, miles per gallon. Because they're on measurement on the same car, these are paired sample. The sample mean mileage was higher after the tune-up. We would like to determine how strong the evidence is that the population mean mileage is higher after the tune-up. These are paired samples because each value before the tune-up is paired with each value of the same car after the tune-up. Matched pair. So how will you do this in the calculator? So first press the second button, then plus on top of enter, then number 4, clear all list, hit enter, done, then stack 1, enter the after, which are higher numbers in L1, which is 35.44, 35.17, 31.07, 31.57, 26.48, 23.11, 25.18, and 32.39. Okay. After we are done with the last data point in L1, hit the right cursor key on the top right corner of the calculator to go to the first line in L2, and then do 33.76 in the second column, which is before, 34.30, then 29.55, then 30.90, 24.90, 30.9, then 24.92, sorry, 24.92, 4.92, then 21.78, 24.3, and 31.25. Okay. Now we want to calculate the 95% confidence interval, or let's see. When we have paired samples, the pairs are called matched pairs. By computing the difference between the values in each matched pair, we construct a sample of differences. So basically, we are interested in the difference between the two measurements, paired measurements. So after we are done with L2, hit the right cursor key so that the cursor is on the first line in L3. Then press the up cursor key on the top right corner so that the cursor moves on L3. Okay, where L3 is written. And then you will type the formula. It is equal to L1 minus L2. So second in L3 where it is written, also notice at the bottom right left corner of the calculator, you have L3 equal to, you do second one minus second two. Okay. And hit enter. And you get 1.68.87. So L3 is equal to second one minus second two and hit enter. Okay. So if we denote the population mean mileage between tune up by mu1 and the two population and the population mean mileage after the tune up by mu2, okay, they are constructing in the difference between. So after I will call mu1 and before we will call mu2, we know after tune up the mileage is higher. So mu1 minus mu2 is positive. Okay. So we are going to perform a hypothesis test on L3. Okay. So what is our null hypothesis? D is the difference, D bar, ST is the mu C. D bar is the sample mean difference between two values in the matched pair. ST is the sample standard deviation of the differences, and mu D is the population mean difference. We have a single random sample of matched pairs. Either the sample size is large, n greater than 30, which is not true in our case, but the differences between the item matched pairs show no evidence of strong skewness and no outliers. This is required to be sure that D bar will be approximately normally distributed. Okay, then we are going to do the test. So in our case, we can test. So we got the differences. We want to check whether the differences uh, do not show any outliers. So L3 is where the differences are located. Now, if you press second y equal to, and then number one, plot one on, okay, put it on, okay, and type the second line, go on the fourth type of chart, which is the first type of box plot. Hit enter so that the cursor in the second line is flashing on top of the fourth chart. Okay. Then press the zoom button, which is the third key in the top row, zoom 9. You should see a box plot without any outliers. Okay. What the outliers, if there are outliers on the left or on the right, it would be shown by a separate box. There are no outliers, therefore we can assume that these differences came from a normal population as is shown in the dot plot in the bottom of the screen here. We cannot do dot plot in our calculator. We have to do a modified box plot, which would have shown any outlier if there was any outlier in the difference. There is none. So now we will do a t-test. So stat. So our null hypothesis is mu d equal to 0. Mu d is the difference between the two paired means. Null is 0. Alternate is greater than 0. Okay. So stat, then highlight test, then do a t-test. Input now should be on data. Mu0 hypothesized population mean difference is 0. List is L3, so second and 3. Frequency is 1. Alternate mu not greater than 0. Okay. So mu d is 0, mu d is equal to 0 is null. Alternate is mu d greater than 0. So put it on greater than mu0 and hit enter. Okay. And then calculate. We'll calculate a test statistic and we'll calculate a p-value. The test statistic is 9.1427 and the p-value is not 1.9, it is 0.0000, 4 zeros and then 19, which is less than alpha equal to 0.05. Therefore, reject the null hypothesis. And at alpha equal to 0.05, there is enough evidence to support the alternate. Okay. Following are the annual amounts of rainfall in inches in 6 randomly chosen cities for 2 consecutive years. Can you conclude that the mean rainfall was greater in year 2 than in year 1? That is, alternate is mu1 greater than mu2. Year 2 we will call number 1. Year 1 we will call number 1. Mu1 greater than mu2. Okay. So, same city. So these are paired measurements. Okay. So second plus 4, clear all list 0, stat 1. So L1 you are going to enter the year 2 data, 34.6, 18.7, 42.6, 41.3, 60.6, and 29.9. Now move to the top line in L2, enter the year 1 data, 25.1, 15.3, 46.4, 31.2, 51.7, and the last one is 24.2. Okay, now move to the first line in L3 by the right cursor key, then the up cursor key, move it to L3. In L3 equal to type the formula second one, L1, minus second 2, L2, and hit enter. So L3 is filled with the difference between mu1 and mu2. Okay, so mu d is basically mu d is in L3. Now, in this case, the alternate is mu d greater than 0, and the null hypothesis is mu d equal to 0. Okay, so stat test, we will do a t-test. Input is on data, mu0 is 0, list is L3. Now our alternate is mu d greater than 0, so mu d greater than mu0, and we calculate. So our test statistic is 2.61, p-value is 0.0237, which is less than 0.05. So reject the null hypothesis that mu d equal to 0, at alpha equal to 0.05. There is enough evidence to support the alternate that mu d less than 0. Okay. Critical value method, we're not interested. I'll not do it. Confidence in paired samples. Okay, same type of deal. So go to stat, test, and we have already data in L1 and L2. Now we want to calculate the 95% confidence interval for difference in the population mean. So go to T interval, scroll down, stat test, scroll down to T interval and hit enter. Input is on data, list is L1, I'm sorry, L3, list is because we are doing 95% confidence interval for the difference, which is in L3, and C level is 0.95, and we calculate. And the interval is between 0.089 and 11.17. So with 95% confidence, we can state that the difference of the rainfalls in the 2 years is between 0.089 and 11.17. Notice 0.089 is on the right of 0 because it's positive. That means mu1 is always greater than mu2. That is, mu d cannot be equal to 0 because 0 is not inside this interval. Therefore, we reject the null hypothesis, much like what we have done before. Okay. I'll not go into this in great details. Too much theory. Okay. This is a to drugs. Group of 5 individuals with a high blood pressure were given a new drug that was designed to lower blood pressure. Systolic blood pressure was meaningful, measured before and after the treatment for each individual. The results follow. Construct a 95% confidence interval for the mean reduction in systolic pressure. So before it was high and after it is low. Okay. So the reduction, so you will see if you call mu1 as before, 2 as after, mu1 is greater than mu2, or mu1 minus mu2 greater than 0. So mu d is greater than 0. And so alternate hypothesis, null hypothesis is mu d equal to 0. So second, plus 4. Clear all list, hit enter, done. Stat 1. So in L1 before, 170, 164, 168, 158, and 183. Okay, then go to the top of L2 and enter 145, 132, 129, 135, and 145. Now we got to take the difference between before and after. So go to the top line in L3, up cursor key to where L3 is written, type the formula second 1 minus second 2 and hit enter. You get the difference in that difference in between x1 bar minus x2 bar. Okay, so x1 minus x2, actually x1 minus x2, and we are going to calculate a 95% confidence interval for the mean reduction. Okay, so 95% confidence interval for the data in L3. So stat test key interval, input should be on data, list is L3, C level is 0.95, calculate. So the lower boundary is 22.34, upper boundary is 40.47. So with 90%, 95% confidence, we can state that the mean reduction in systolic pressure is between 22.34 and 40.46, which is greater than 0. Okay, hence we can reject the null hypothesis that mu d equal to 0. Okay, and support the alternate that mu d is greater than 0. Okay. Okay, now let's go to the last one. Inference about difference between two proportions. Perform hypothesis test for the difference between two proportions using the p-value method. Perform a hypothesis test for the difference between two proportions using, I'm not doing critical value, confidence interval difference of the two proportions. Okay. The General Social Survey took a poll that asked 350 employed people aged 25 to 40 whether they used a computer at work, and 259 said that they did. So the proportion of people in the age group 25 to 40 who used who used a computer is 259 out of 350, which is 0.74. And the proportion of people in the age group 41 through 65 who used a computer is 384 out of 500, which is 0.768. The sample proportion is larger among older workers. The question of interest, however, involves population proportions. There are two populations involved: the populations of all employed people aged 25 to 40 and the population of all employed people 41 to 65. The question is whether the proportion of age 41 to 65 who use a computer at work is greater than the proportion among those aged 25 to 40. This is an example of a situation in which you have two independent samples involving sample proportions. Okay. So the notation P1 and P2 are the population proportions of the category of interest. P1 hat and P2 hat, those things in the top are called hat. Their sample proportions, X1 and X2, number of individuals in the category of interest, sometimes called successes in the two samples. N1 and N2 are two sample sizes. So the null hypothesis is P1 equal to P2. Alternate can be a left tailed, a right tailed, or a two tailed. Okay. And then you have the standard deviation of the sampling distribution, standard error, all those things. I will not worry too much about it. Let's jump to a problem. Okay. Same problem. The General Social Survey took a poll that asked 350 employed people whether they used a computer at work, and 258 said they did. They also asked the same question of 500 employed people aged 41 to 65, and 384 of them said that they used a computer at work. Can you conclude that the proportion of use a computer at work is greater among the 41 to 65 than those? So we will call 1 as the group with age between 41 and 65, and 2 as the group with age between 25 and 40. And we have to calculate or then alternate hypothesis is P1 greater than P2. Null hypothesis is P1 equal to P2. So let's get our calculator on, stat, test, and we are doing a 2-prop Z test, 2-prop Z test, okay? So X1 is the number of success in sample 1, which is the higher age bracket. So 384 X1. Of them said they used. N1 is 500. X2 is the other group, and their success is 259. And the sample size N2 is 350. Okay. So we want to test whether P1 is greater than P2. So the alternate is P1 greater than P2. We'll calculate a test statistic, find a p-value. P-value test statistic is 0.936, p-value is 0.1746, which is greater than alpha 0.05. So the decision is do not reject H0. So at alpha equal to 0.05, there is not enough evidence to support HA that P1 greater than P2. Let's see what did they conclude. Yeah. Do not reject H0, and we cannot support the alternate. Okay. In a criminal trial to compare the effectiveness of two pain relievers, a sample of 100 patients was given drug 1 and an independent sample of 200 patients was given drug 2. Of the patients on drug 1, 76 experienced substantial relief, while the patients on drug 2, 128 experienced substantial relief. Investigators want to know whether the proportion of patients experiencing substantial relief is greater for drug 1. Okay. Okay. Drug 1 is greater. Okay. So 1 is drug 1, 2 is drug 2. So the alternate hypothesis is P1 greater than P2. Null hypothesis P1 equal to P2. So stat, test. How do I know this is a proportion test? Because there are two sample sizes and two groups of successes, X1 and X2. Remember, X1 number of successes, people who are getting relief. Okay, so two sample, 2-prop Z test. Okay. X1 success in group 1. Okay. In of the patients on drug 1, 76 experienced. So and X1 is 76. Sample size is 100 N1, group of 100 patients. X2, those who got relief in group 2. Okay. Well, of the patients on the drug 2, 128. Sample size is 200. Okay. We want to test whether P1 is greater than P2. Okay, so alternate is P1 greater than P2. Then we calculate a test statistic, 2.10, p-value is 0.0178, which is less than 0.05. So we reject the null hypothesis that P1 equal to P2 and support the alternate at alpha equal to 0.05, that P1 greater than P2. So we reject. Okay. Difference between two proportions using the, I'm not using critical values. And then there's a question of confidence interval. So let's look at this one that we just now did. Okay, so we did that. Okay, so we rejected the null hypothesis. That is P1 equal to P2 or P1 minus P2 equal to 0. We rejected the null hypothesis. Let's check it out. So if we rejected the null hypothesis, P1 minus P2 equal to 0, that is P1 equal to P2. 0 should not be inside the 95% confidence interval. So we do stat, test, and we are going to go to 2-prop Z interval, 2-prop Z interval. Okay. X1 is 76, okay, out of N100, X2 128 out of 200, C level is 0.95, calculate. We already have rejected null hypothesis, that is P1 equal to P2. We have rejected it. That means P1 minus P2 equal to 0. We have rejected it. So 0 should not be inside the 95% confidence interval for the difference in the two population proportions. Let's calculate and see. Notice the lower boundary is 0.013 and the upper boundary is 0.227. 0.013 is on the right of 0 being positive. Hence, 0 is not inside the interval. Therefore, we can safely reject the null hypothesis and support the alternate hypothesis. That's what they're talking about in this case. I will not go into too much details because the details are crazy. Okay, let's do this one. Random sample of 50 children living in a community with highest level of ozone pollution had their lung capacities measured, and 14 of them had capacities that were below normal. A second random sample of 80 children were drawn from a community with a low level of ozone pollution, and 12 of them had lung capacities that were below normal. Construct a 95% confidence interval for the difference between the proportion of children with diminished lung capacity between the two communities. So let's call the one with no pollution as sample 1, okay, and sample 2 is the community with high pollution, okay. So stat test, we scroll down to 2 prop z interval and hit enter. So my x1 is the, remember 1 is the community with uh, low pollution. So x1 is 12. We can call x1, uh, let's call 1 as the community that is having a high level of pollution. So success in that community is 14 of them had high level of pollution, have capacities that were below normal, 14 children, and N1. So 1 is the community that have high level of pollution, and N1 is 50, X2. X2 is the other community with low level of pollution. So X2 is 12 and N2 is 80. Here I'm going to test whether P1 equal to P2. That's the null hypothesis. Alternate is P1 less than P2. Okay. So C level is 0.95 and we will calculate. Notice the lower boundary is minus 0.017, which is on the left of 0. And the upper boundary is 0.277, which is on the right of 0. But 0 is inside the interval. So P1 minus P2 equal to 0, that is P1 equal to P2 is the null hypothesis. We cannot reject it. Okay. Therefore, there is not enough evidence to support P1 is less than P2. Okay, let's see what they calculate. Yep. The confidence interval contains 0. Therefore, we cannot be sure proportion of children with diminished lung capacity differ between the two communities. That is, we do not reject H0P1 equal to P2. Okay. So I'll stop here today. We can do this one if you like. A class of 30 computer science students were taught introductory computer programming class with an innovative teaching method that used graphical interface and drag and drop method of creating computer programs. At the end of this class, 23 of these students said that they felt confident in their ability to write computer programs. Another class of 40 students were taught at the same material using standard method. And the end of 25 At the end of class, 25 of the students said they felt confident. Assume that each class contained a simple random sample of students. Construct a 95% confidence interval for the difference between the proportions of students who felt confident. So 1 we will call the new method, 2 we will call the old method. Okay. So stat test, and we scroll down to 2 prop z interval. Hit enter. X1 23 is the new method, 23 out of 30. So N1 is 30. X2 is the old method, 25. out of 40. Sea level is 0.95. Calculate. So it is between minus 0.07 and 0.355. With 95% confidence, we can say the difference in the two population proportions will be between minus 0.07 and 0.355. 0 is inside the interval. So we cannot reject the null hypothesis that P1 minus P2 equal to 0 or P1 equal to P0. Since 0 is inside the interval, we do not reject the null hypothesis. Therefore, at alpha equal to 0.05, we do not support the alternate hypothesis. That's it for today. If you have any question or concern, just shoot me an email and I'll get back to you as soon as possible. Thanks for watching and have a nice day. Take care. See you next time.